a special session of the spring break. So we have a Merlin Christ telling us about Perverse schober from Lefschetz.
Yeah, thank you very much. Also, particular thanks for coming here during the spring break to the talk. So yeah, I will talk about these perverse schobers, which are categorified perverse sheaves. I'll explain that a bit later, and how they specifically arise from Fukaya categories from Lefschetz fibrations. Let me be a bit general. First, so you have the A model in string theory, and this is a topological theory. So what does that mean? I'm sure the physicists have somehow a much maybe different or better understanding of this, but what it means to me is that it should behave, well, first I should maybe say what its mathematical version is. So mathematically, it's the, this describes the Fukaya category or the Fukaya-Seidel category. Fukaya category or the Fukaya-Seidel category. So these are triangulated or infinity categories arising from this physics, essentially. And the question is, what is the mathematical property of these theories, which reflects that this topological theory is that this physical theory is topological? And how I think about it is that it behaves similar to topological cohomology. So topological means behaves similar.
It's actually not at all what physicists mean it's topological. They mean it's topological the surface, right? It's topological the Riemann surface, not the target.
This is topological on the surface.
I mean, the signature of the being topological on the world shape is that you actually work with a, I argue with kind of endlessly, with a derived type vector, with a cosmology vector, not with a simple working vector.
That has nothing to do with cutting off the target.
No, it has nothing.
But the topological in physics, and when they say it's topological twist, does that refer to the target? They mean the wall sheet.
The domain curve, yeah.
The domain curve, as I would be.
Yeah, and you would expect that
excellent.
You some topological information on the target. But
Right. Sure. Okay, great. Yeah, if I say nonsense about physics, or especially maybe symplectic geometry later, yeah, as we have some experts, please correct me. So it behaves similar to singular cohomology, or well, let's just say topological cohomology. And maybe the favorite way to compute topological cohomology is sheaf cohomology. Yeah, does the Fukaya category form some kind of sheaf? And there's of course an answer to that, or some type of answer by Ganatra-Pardon-Shende about cosheave descent. Cosheave descent. So in some sense, the Fukaya category behaves like a cosheave of categories, and the idea behind that is the following: you have, say, you have a symplectic manifold Y with a fibration pi to a surface. Then surface with boundary. Then how do you compute the singular cohomology of Y, or the sheaf cohomology of Y? So the cohomology of Y with coefficients in C, this is equivalent to the derived sheaf cohomology on C of the constant sheaf of Y of the constant sheaf, and this is equivalent to the sheaf cohomology of the base S with valued in the push forward sheaf. Right. So you can compute the cohomology of the total space in terms of the cohomology of the base with coefficients in a different so here you have the constant coefficients, and here you have non-constant coefficients in a sheaf. And this picture we want to categorify, or at least partially categorify. So this is partially categorified by saying that, well, so we don't know how to categorify all of the cohomology of the total space Y. Let's say this is a symplectic manifold. symplectic manifold. And this is a Lefschetz vibration. But we know how to categorify part of the middle cohomology, the Hn, where it's an two n manifold. So dimension is 2n. Then you have the Fukaya category of Y. This partially categorifies the middle cohomology, and you want to express that in terms of a type of sheaf cohomology on the surface. And what we'll say here is that it's the some type of 1 degree in the sheaf cohomology of the surface with values in a R pi star of the derived category of C. So instead of taking a sheaf of vector spaces, you're taking a sheaf of categories. The stalk will be the derived category of the field C, and you're pushing that forward, and we put the n here. And then we don't have a systematic way to categorify the entire push forward, but maybe part of that, which gives us a perverse sheaf of categories. Sheaf of categories. And then you compute the global sections of this sheaf of categories, and you get the categorification of the sheaf cohomology, which is the Fukaya category. And such a sheaf of categories is called a schober. So this is a schober. So schober is a German word. It means haystack. And you know, a stack is a sheaf of categories. So schober is German for sheaf of categories. And this, of course, is somehow the idea behind these constructions. Now I'll try to somehow make actual mathematics out of this proposal of like categorifying sheaf cohomology. Right. And well, S will be a surface with boundary, right? Topological surface with boundary. It's a topological theory, so you don't need a smooth structure. High dimensions? Yeah, that would be nice to have. Yeah, but it's hard. I'll maybe say a little bit about that at the very end. In general, somehow the setting of categorifying sheaf cohomology, it works particularly well for, there's quite a worked out theory for surfaces, and at high dimensions there are many challenging questions which remain open, and we'll have to see when they're solved and how they're solved.
But you'd imagine that any time you have a category of vibration, you can always describe it as a category on the base.
That would be the general proposal that that's true, yeah. The general expectation. Absolutely.
There's a version of the rest spectral sequence.
Of which spectral sequence?
The rest spectral sequence.
Well, I don't know. Yeah, I don't know too much about spectral sequences, so yeah, I'm not sure.
No, but like the rest before is like formalism, like
Right. So one point here is that also, so the Fukaya category is just one category, and it's not a sequence of categories. And the cohomology groups are a sequence of groups, which would be categorized by a sequence of categories. So we're somehow only categorizing one summand of these cohomology groups. And it's also unclear what the so if you take the push forward, that's a complex of constructible sheaves, where it's somehow only categorizing one degree or maybe one cohomology in there, which is then a perverse sheaf. Shifted maybe in some degree here. So, but yeah, so it's, I don't know how to answer your questions. I guess the answer.
I guess like this Argama on the outside. Or like it is in oscillation.
Yeah, I think I took the homology here, so I can remove the R there. Yeah, exactly.
This question on the right makes this procedure especially suspect, because usually if you want middle cohomology of the total space, then you need, different degrees of base and phi rallying up the middle. And here you're only taking middle degree of the phi.
But we're also taking the middle degree. Well, yeah. So I'll make this precise later. How this is done. This is by working with relative to a skeleton. You're not computing just arbitrary sections, but sections with support on a skeleton. And then actually, the thing you categorify is the first relative cohomology with support on the skeleton. I'll explain that later. Yeah, so that's something I swept under the rug here. Right. And then the dimension set up. Any other questions before I? Okay, excellent.
Is it sufficiently clear that Rn and star denote some kind of forward?
I mean, there's no systematic way to define this. That we just, that's basically an ad hoc form. Well, more or less ad hoc formula. Yeah. Okay. So so far for the overview. So I'll begin by explaining, or since we have a mixed audience, I'll first recall the construction of the Fukaya-Seidel category. Then I'll explain to how to get that from a sheaf of categories. So just a schober. And afterwards, I will explain why this schober is actually perverse. It's a perverse schober. What it has to do with perverse sheaves, and then we'll see maybe what you can do with that afterwards. Right.
But the option of the comment is that the surface case, Riemann surface case, and the symmetric rise is special. Because otherwise you'll have the problem with the table. You want to combine the Lagranges and the
Degree 0 in the base and degree +1 in the final. Not for duration.
Well, you solve this by only computing those cohomologies which turn out to be concentrated in a single degree. By only working with someone with specific.
When you explain how to
yeah, let's see if we learn how that works later. So let me recall somehow this construction of the celebrated Fukaya-Seidel category. Somehow very computable, appears a lot. So the setup, you have a Lefschetz fibration, fibration over C with, let's say, the fiber and the regular fiber at infinity is called F, and let's say X is 2n dimensional, exact symplectic, and yeah, maybe need some more data, but let's maybe stick with that. And you have the Fukaya-Seidel category of pi. I'll define it in a minute. What it does for you, it interpolates between the Fukaya category of the fiber, or depending on your setup, the rep Fukaya category of the fiber, and the rep Fukaya category of the total space, or the Fukaya category of the total space. So if you, what it does for you, this Fukaya-Seidel category, which is very explicitly computable, I'll define in a minute, is if you know the Fukaya category of the fiber well enough, you can compute this category, and the Fukaya category of X can be recovered from this category. So this gives you a maybe inductive way to compute Fukaya categories by describing them in terms of Fukaya categories of fibers, which are 2 dimensions smaller, 1 complex dimension smaller. So how this works is, or how to define the Fukaya-Seidel category, you have here C, or point at infinity, and you have some singular values, V1, V2, Vn, the singular values of the Lefschetz fibration. And for every singular value, there's a unique vanishing cycle. So you have to choose a path to connecting your singular value with infinity, and then you have the vanishing cycle, which is a Lagrangian sphere. Lagrangian sphere Si in let's say in the Fukaya category. Let me from this point onward just work with rep Fukaya categories. So in the rep Fukaya category of the fiber, and the way you define the, let me see, does this fit there? Probably not. And let me go to a new board. Is there? Oh no, this is already perfect. Okay. So I have these vanishing cycles, and the Fukaya-Seidel category is the, or at least this is maybe the most classical construction of this category due to Seidel. It's the directed A infinity category on the SIs. So what does that mean? Let me define it explicitly. The objects are Si tilde, where I goes from 1 to n. So these are the thimbles. Algebraically, they're just the same objects, maybe with a decoration on top. But geometrically, you like to think of them as the following. So here you have infinity, then you have your path connecting the singular to the singular value. In the fiber here, you have a sphere, which when you transport it along the path, it collapses. So this would be Si, and this entire thing is the thimble, Si tilde. So that's maybe the geometrically how you think of these objects, but this is a purely algebraic construction. So these are the objects, and then the homs. So the R hom from Si tilde to Sj tilde in the Fukaya-Seidel category. This is simply, so first if I is equal to j, it's k, so they are exceptional objects. If I is less than j, then you take the R hom in the Fukaya-Seidel category, sorry, in the Fukaya category of the fiber, or in the rep Fukaya category, not really relevant, Sj, and it's 0 if I is bigger than j. So you have a directedness condition that the homs somehow only go from left to right between your different thimbles. And clearly this is somehow very explicit. Very explicit. And that's one of the main reasons I think that Fukaya-Seidel category is so popular, because it's somehow a really hands-on construction as an infinity category, using some directedness construction like that. And as I said earlier, you can compute the rep Fukaya category of X or the Fukaya category of X from that category. Maybe one thing I want to tell you about before we come to how to describe this category in terms of sheaves or categories is an interesting construction of Lagrangian spheres in the total space, which you can do in this context where you have a Lefschetz fibration. These are matching spheres. If I is equal to j, it's just, C. Let's say we're working with the complex numbers. K is when I write K, I always mean a field. I guess we can just assume they were complex numbers today. So matching spheres are the following. When you have, in the case that Si is equal to Sj, where I is not equal to j, we have, there's a morphism from Si tilde to Sj tilde, right, which is the identity on Si. So if, where, let's say I is less than j. So I'm assuming two of the vanishing cycles in the fiber, they are the same sphere, but I think of them as different thimbles. Then in the Fukaya-Seidel category, there's a morphism from the one thimble to the other, which is just computed via this formula as a morphism in the fiber. In the fiber, it's the identity. I can take the cone. The cone, let's call this S. And turns out that in this case, S is a Lagrangian n-sphere in X. So Si and Sj are Lagrangian n-1 spheres, and well, the same Lagrangian n-1 sphere, and I get a Lagrangian n-sphere. What is the picture for this construction? So you have two singular singularities, singular values, and you have these the vanishing cycle and the generic fiber. And when you transport it along the along this path, it collapses at both ends. And topologically, if you look at that with where you take the parallel transport of the sphere, this is a suspension of the sphere, which is a sphere of one dimension higher. So this is how you one somehow very nice and popular geometric construction of Lagrangian spheres in the presence of Lefschetz fibrations. And why is it the cone of the two thimbles? How you think of that is maybe you have this thimble and the other thimble, and they correspond basically to let's see if I can draw that. This is one thimble, and this is the other thimble. And by taking the cone, you're smoothing out the intersection, and then you get the top thing. Up to homotopy, yeah.
How sure are you with the tone of the identity as opposed to fundamental ones?
Well, the point is that in the fiber, you want so there's an exact functor to the Fukaya category of the fiber, and there you want the image to be 0 of the matching sphere. Yeah, you want to cancel it, right? Thanks for the question, though. Great. So this is what somehow maybe a non-expert introduction to Fukaya-Seidel categories, which we'll now want to look at from a very different perspective, which are no, just some class, but they're particularly nice. They're easy to. There's like a concrete way to construct them, and in many examples they're very important. And it's like a very popular construction, and we'll later see a way to construct these spheres in a categorical way. That's why I'm recalling this now here, because later I'll explain this, how to get this from sheaf theory, this construction. Yeah, okay. Other questions? Let me continue here with sheaves of categories. So first, I want to talk a little bit about constructible sheaves. What we want to do, so where do we want to have a sheaf? And we have this picture here. And we consider this actually the union of these we can consider this as a graph which has vertices. There's vertices v1, v2, vn, and the vertex v infinity, and it has edges, which are these paths. So this is a graph G. Graph G. I want to describe the Fukaya-Seidel category in terms of a constructible sheaf on G. So what's a constructible sheaf? This is it's a sheaf which is locally constant on every edge. Every edge. So what does that mean? Somehow I have a stalk at each vertex, and then on the edge is contractible and it's constant. So the sheaf is determined by any stalk on the edge. So, and then there is restriction maps from the vertices to the edges. But a constructible sheaf on a graph is kind of a very discrete combinatorial type of datum. And this is encoded by the following theorem, Telluri and others, that constructible sheaves on, say, G, valued in any, say, category or infinity category. If you're not familiar with infinity, just think of category. This is equivalent to functors from the exit path category of G into C, the functor category. So what does that mean? Let me explain what the exit path category is in an example, and then I think it will be clear what I mean. So example, let's say G is not the graph in our, I guess in the case where you have a unique vertex V1, let's say it's this graph, V1 and V infinity, then the exit, V infinity, and this is E. And the exit category of G is, it has 3 objects, namely V1, V infinity, and E. And the morphisms, they go from the 2 vertices to the edge. This is a category with 3 objects and 2 non-identity morphisms. This is, it's also a poset if you want, partially ordered set. And a sheaf on this graph, it will be a functor from this category into C, and it's then just a diagram, V1, F, V infinity, and Fe, together with functors or maps between them. And this is the stalk at V1. This is the stalk at V infinity. And so a sheaf is such a diagram which has 3 values and 2 maps, and Those two are the stalks at the vertex, and this is maybe the sections on the edge, sections on E. And the theorem is that this datum, these stalks and restriction maps, they fully encode my constructible sheaf. So it's a general abstract nonsense result. Say again? Yeah, the functors are arbitrary, exactly. The values and the functors, so this would be a diagram in C. The theorem is an equivalence of categories between constructible sheaves on the graph, which are sheaves which are constant on the edges, with functors from the exit category into any category C. So C could be vector spaces. And then this would be a diagram of 3 vector spaces and 2 linear maps. And I'm saying a constructible sheaf of vector spaces on the graph is the same as this datum, which are the 2 stalks at the 2 vertices, which are 2 vector spaces, and the sections with living on the edge, which is another vector space, and the 2 restriction maps, which also come from the sheaf data. C, it's a constructible sheaf valued in the category C. Exactly. You're saying if these are vector spaces or greater vector spaces? For instance, yeah, if I say C is the category of categories, right? Yeah, in a minute C will be the category of categories.
If you have the same picture in drawing, and your sheaf has sections here, sections here, sections here. So there's a map, sections here, sections here.
How do I?
Right, but like, let's classify like if I want to say like what the surface left,
But the proof of this theorem is.
no, I'm not interested in the proof. I want to look at this specimen. If like C is left, like what? What is this specimen?
This example.
Yeah.
The representations of the A.
I don't think so. Let me maybe continue, and I think it will be clear in a minute. So let me also tell you what is the global sections of the sheaf from this diagram. I should have written this here. So the in this case, the pullback of this diagram is the global sections. Yeah, you have 2 maps. You can take the pullback, and that describes global sections. Okay. Now we want to specialize to the case. So yeah, I'm covered. Let me rewrite it here. So you have f of v1, f of v2, fe. This corresponds, as Vivek pointed out, this is, you take this covering of the graph. Sections which support on here give you fv. This gives you fv prime, v2, v1, and then the sections on the overlap give you fe. And the sheaf condition tells you that the pullback here, this is global sections, gamma on GF. Excellent. And it doesn't matter what these things are. I'm taking the pullback in C. C can be vector spaces. C can be the category of categories, if you want. And now C will be DGCAT or stable. So the category of DG categories or the category of stable infinity categories, whichever you prefer. And then you can still, the constructible sheaves are not sensitive in this description to where they live, where they're valued. Right. I hope that's more or less clear. So this is the case of schobers. So a schober is a sheaf of categories. Specifically, it's a sheaf of like triangulated categories or enhanced triangulated categories, which we model by DG categories or stable infinity categories. So when we're talking about schobers, we're talking about constructible sheaves valued in this. Okay. Now, now I want to define a schober on. So we had this picture here, V1, Vn, V infinity. I want to define a schober on this graph, giving you the Fukaya-Seidel category. So, first of all, f of Vi, we set this to be the derived category of the field. Sorry, that's just complex numbers. F of E, let's call this E1 and this En. F of EI, this is just the derived wrapped Fukaya category of the fiber. And F of V infinity, this we will define as the derived category of the wrapped Fukaya category of F tensored with the AN quiver. Or if you want, this is maybe derived representations of the AN quiver in the wrapped Fukaya category of the fiber. There are ways to make this precise. I don't want to be over precise here. There's two ways to describe this categories. Category one is by tensoring with the AN quiver, which is the linear quiver 1, 2, N. Or you're taking representations of that quiver in the Fukaya category of the fiber. And then there are functors, right? So the restriction functors, what are they? So here, this is tensoring with Si, which was my vanishing sphere, my vanishing cycle. And this functor here, I don't want to describe it quite yet. I'll do that a bit later. It's some kind of projection. So there are at least n projections from here to there. I'll say which ones later. And you use these to define a sheaf. And let me explain to you why this sheaf, its global sections, are equivalent to the Fukaya-Seidel categories. Theorem, gamma GF, so global sections. So I have a constructible sheaf of categories, meaning the global sections themselves form a category. And this category is equivalent to the derived Fukaya-Seidel category. So how do we prove this? So first of all, we want to use Ganatra-Pardon-Shende cosheave descent. Cosheave descent, what does that tell us in this situation? So we take a decomposition of the n-gon, it's the one-gon. Here we have our singular values. We're decomposing this into sectors, where this is C greater equal than 0. This is a half plane, and this is what is called an AN sector, meaning that it's the wrapped Fukaya category of this sector is the AN quiver, derived category of the AN quiver. And what we're now doing with this decomposition of the disk is we're pulling it back along the Lefschetz fibration. So if you take pi inverse of C greater equal than 0, the wrapped Fukaya category of this will be the derived category of the field, up the derived wrapped Fukaya category. And the let's call this sector maybe some name B, and the derived wrapped Fukaya category of the inverse image of B will be equivalent to this category over there, the AN tensor product. Should follow from a type of König formula. And then, the Ganatra-Pardon-Shende cosheave descent formula tells us that the theorem is true for cosheaves. So gives us the theorem for cosheaves. So what's a cosheave? The difference between a sheaf and a cosheave is that instead of restriction maps, you have co-restriction maps. Do we still have? Yeah, let me maybe go back here and. It's an AN quiver. AN is the AN quiver. A fine one? No, no.
Why is the last stop different from the others? What breaks the symmetry of the
You're just choosing a set of generators. I'm breaking the symmetry. So if you want the generators, in the A3 case, it would be these three which I choose. And
so that's what you call the actual, the corresponding unlike quiver to F line.
No. The drive category, the usual and back has a second set. And moreover, it's over this.
right. Thank you. So this they're working in the setting of cosheaves instead of sheaves. What's the difference? So while the sheaf is a functor out of constructible sheaf is a functor out of the exit category, a constructible cosheave. So cosheaves constructible on G, valued say in stable, they are equivalent to functors out of the exit category of the graph into stable, opposite. So this opposite is not important. Focus on this one. So whenever I had before I had morphisms going from vertices to edges, now they go from edges to vertices. They are, instead of restriction maps, I have co-restriction maps. And they would, the Ganatra-Pardon-Shende cosheave gives you such a, once you derive it, it gives you such a constructible cosheaves of stable infinity categories. And then its global sections give you the Fukaya-Seidel category. And now, how to go between sheaves and cosheaves? This is by, so sheaves, cosheaves. You pass between these two worlds by passing through the adjoint diagram. And so all these functors which we have here, they have adjoints. So for instance, in this picture, if I had my sheaf before, it would arise by passing to the right adjoint functors here of the cosheave. So my cosheave has two functors like this. Sorry, it was in the wrong direction. And then I take every functor in the diagram, I pass to the right adjoint. This gives me now, this turns around the direction of the arrows. Hence, from a cosheave, I pass to a sheaf. And then Lurie proved that in a suitable setting that that this sheaf-cosheave correspondence, this is compatible with the passage to global sections. So global sections compatible with sheaf-cosheave duality.
By this you mean that Lurie proved that PRL and PRR.
Right, exactly. I don't want to be technical. It's something about presentable infinity categories and limits and co-limits. The global section of a sheaf is the limit. The global section of a cosheave is a co-limit, and they agree by passing to the adjoint diagram. It's some general abstract nonsense category theory. So, but I want to insist working with sheaves. It will be clear later on why. But I'm just saying that somehow the cosheave theorem is as good as the sheaf theorem in this regard. So again, they're derived.
So here we have like very specific partners.
Explicit. Oh yeah, in this case, what they are?
In this case, yes.
Yeah. So one of them is the adjoint here is R hum out of SI. Right, that's the right adjoint. And this functor I didn't define, so I want it's some fully faithful functor. Yeah.
And also,
You're
So I know Ganatra-Pardon-Shende descent as like in the context of Weinstein coverings. I imagine from your picture the argument you apply is that you cover the base, and then you lift that to cover.
Yeah, you pull back the cover of the base to the total space.
Then it works.
if I'm naive, so I know like that definition of board,
Right.
can I use that to check its directly?
Yeah, so that's maybe on the level of infinity categories, this is at least not written down, probably possible. on the level of homotopy categories, I mean, you can compute this limit of these categories explicitly, and then check that it somehow gives you the same thing, the same formulas for homs and so on. It's that I would need to explain a little bit how you compute limits of categories, but essentially, I mean, what you see here you have this type of directed category. This is a directed category on the fiber, and then by pulling back, so this is the value here, and then here you have the derived category of the field, and by computing the limit over this diagram, what you're doing is you're taking the full subcategory of this category on the vanishing cycles. This is really what the limit diagram is trying to tell you, which is exactly what Seidel defined the category to be. So yeah, this directedness is intrinsically built into this formula.
Directedness is the same.
Exactly, that's the directedness.
Yeah, and then like part is degraded by a side.
Yeah, because that's how you compute the limit. Yeah, there's something you have to check computationally, but you can check it. Yeah.
Okay, so if we can prove it, like maybe modulo is like
modulo A infinity, it's definitely clear that the Schober construction gives you the Fukaya-Seidel category in the sense of Seidel, or other version would be to prove it by a cosheaves descent. Yeah. Both valid ways to prove it. So next, I wanted to maybe first. So next, I'll explain that this sheaf of categories, this schober, is actually a perverse schober. So F is a perverse schober, not just any sheaf of categories. It's actually somehow perverse in some sense. And afterwards, I'll explain why I want to work with sheaves instead of cosheaves and what you gain by working with these. Right. So let me begin by recalling how perverse sheaves on C work. How do you spell perverse like this? So perverse sheaves on C, there's the following very classical theorem, going back to at least Galigo, Granger, Maisonneuve, 85, is that, so if you have perverse, the abelian category of perverse sheaves, I won't define it to you, I'll only describe it now, which is this theorem. So you need to give a stratification of the space. So I'm thinking of C as stratified by 0 and the complement of 0. This category is equivalent to the following category of diagrams of vector spaces. You have the vanishing cycles, phi, and the nearby cycles, psi, and two maps. So this is a diagram of vector spaces. Which satisfy the following, namely Fg minus the identity on psi and Gf minus the identity on phi are invertible. This is a very. This is how you can, without me telling you some more reasonable definition of perverse sheaves on C, I can define them like this using this description. So what are phi and psi? So say I fix a perverse sheaf here. Perverse sheaf. I need to draw the following picture. So you have C, you have here 0, and first of all, if we restrict F to C star, this will be a locally constant sheaf, a local system. And let's just pick a point P here, and then psi is the stalk, Fp, the nearby stalk. It's the nearby cycles. And to describe the vanishing cycles, maybe I want to choose P in the complement. Maybe that's more honest. So to describe the vanishing cycles, I need to choose a graph, as we did before. Like that, let's choose this graph. So we can describe phi as follows. The vanishing cycles, they describe the cone from the global sections are gamma of the sheaf on C. These I can restrict to the stalk FP, to psi. This is restriction. And if I take the cocone of this, or the cone, maybe I take the cocone, this will be my vanishing cycles. And so this is a priori a chain complex of vector spaces, but it turns out this is concentrated in a single degree. So this is chain complex in degree 0, concentrated in degree 0. It might be degree 1 or -1. I think it's 0, but I might have messed that up. And you can describe this equivalently in terms of the derived sections.
What is that symbol?
Which one? R gamma?
No.
Res? Psi? Equivalent?
No.
Cocone?
Maybe.
Complex? Chain complex?
No.
Concentrated in degree 0.
The one saying R gamma is on this symbol.
C? Yeah, we're on the complex. C is our disk on which we are. We're describing Perverse sheaves on C. Complex numbers. Just the disk. Yeah. So this you can equivalently describe as derived global sections with support on G. So support.
Now it's like G the complex numbers.
Yeah, I'm. Okay, so you have your complex numbers, and you chose a skeleton, which is this graph, and your vanishing cycles describe the sections with support on this graph, which by general abstract constants, the way you compute that is by computing the difference between global sections and sections in the open complement. And sections in the open complement, because it's contractible, are equivalent to the generic stalk, FP. So, and the difference is taking the cocone. So what I'm saying here is that you can describe your Perverse sheaf on C. P is a random point which is not on the graph, maybe. Yeah, it's not 0. That's the main thing which it needs to satisfy. Because so F restricted to C star, it's locally constant. So any stalk will be equivalent, right? And I can also tell you what the monodromy is in terms of this description. This has monodromy. The generic stalk, and the monodromy is the identity minus FG. So in this description, to understand my Perverse sheaf, I need to know the generic stalk. I need to know the sections on the skeleton. Then there are 2 maps, which there are some type of restriction maps. Let's not worry about that. And they satisfy 2 conditions. And these conditions describe, well, the first one describes the monodromy of the local system on C star. The second one, this is an autoequivalence of phi. This comes from rotating the skeleton. If I rotate G once around, I get an autoequivalence of the category of sections on G, and that's this on the vector space of sections. Yeah, and this is this automorphism of the vector space. Right. So. So one thing I want to point out about this is that this description is actually gives you a sheaf and co-sheaf on the graph. Not at all. The point at infinity is really not special, actually. It's your choice of skeleton is special at infinity in that example, but I'll explain that. Maybe that will be clear maybe in a minute when I said something else. So sheaf plus co-sheaf on G. So you have phi, psi. So a sheaf on this graph is 2 vector spaces and 1 map. A co-sheaf is 2 vector spaces and a dual map. It's sheaf co-sheaf pair. So I'm describing my Perverse sheaf F in terms of a sheaf and co-sheaf on this choice of graph. And then, is there anything else I want to tell you about that? Yeah, let's do an example.
Fukaya-Seidel categories are just one very special example. We know that there are many other is it going to be the case that you'll be able to describe schobers in this setting?
In Fukaya-Seidel categories.
Work with that setting.
Right, right.
Right now, you're providing a definition of schober.
Oh, I will give a definition of schober which is more general.
I know, but what he's doing right now is providing us a motivation and a definition.
Right. Yeah, I'm explaining what perverse sheaves are. Explaining something else in a minute about choosing a different skeleton on the disk, and then we'll categorify that and get the notion of a perverse sheaf of categories, and then we'll see that the Fukaya-Seidel category comes from a perverse sheaf of categories. Okay, let's say what is the constant sheaf? Constant sheaf C with you have to shift in degree for some to match the usual convention for perverse sheaves. Okay, now I have to insist that my field is not the complex numbers because otherwise we'll get confused. So I have the constant sheaf valued in the field K on C. This is a perverse sheaf. This is in perf of C. And under this theorem, this corresponds to the following pair of vector spaces. The nearby cycles are just the field, and the vanishing cycles, the zero. And of course, the identity minus the composite of the 0 and 0 map is the identity, which is invertible. Okay, that's the example. And then next, for different skeleta, you have a generalization of this story. So we want to now look at the so-called N spider, which looks as follows. 1, 2, 3, N. You have N legs instead of one leg. And then there's an analogous description of the category of the very same category. We're not changing the category of perverse sheaves. We're only changing our description on it using a different skeleton. So theorem due to Kapranov-Schechtman. Perverse sheaves on that are equivalent to the following. So you have, let me use maybe more geometric, slightly different notation. Or let's call phi n, psi I. You have linear maps fi and gi. And now you have n such diagrams. So you have n linear maps going this way and linear maps going this way. You have one category in the middle, and you have n categories here. So again, we have a sheaf, co-sheaf type thing on the graph. Here we have phi n, here we have psi 1, psi 2, psi 3, and so on. And then there's all these maps, restriction, co-restriction maps. And then they satisfy some conditions. So first of all, if you take Fi-Gi, this is the identity on psi I. Fi-Gi plus 1 is invertible. And Fi-Gj is 0 otherwise. So if it's not I plus 1 or j is not I plus 1 or I. These are some linear algebraic conditions which you impose on such a diagram. And then the statement is that the perverse sheaf is captured by this. And what is phi n? So here F is mapped to some such datum where phi n is again sections, global sections, derived global sections of C valued in F with support on the n spider Gn. These vector spaces psi I, they're again the generic stock away from 0, but they're all equivalent, right? Because these maps are invertible. This map identifies psi I with psi I plus 1. And then the category in the middle, the vector space, I'm already categorifying. The vector space in the middle is sections with support on the graph. Okay. And we are free to choose any skeleton we want somehow to get this description of perverse sheaves. So now let me try to categorify this. well, I guess also succeed in categorifying this. Categorification. So what's the philosophy more generally for the categorification? So we have vector spaces, and we categorify them in terms of, say, enhanced triangulated categories. Triangulated. So for me, my favorite enhancement are stable infinity categories. You can also work with DG. And then you go back by taking the Grothendieck group K0. And then one other thing I need to tell you, when you have a difference, so let's say you have a vector space V and you have two elements, and you can form the difference of two elements in a vector space. How do you categorify this? Because
This word of categorification is so terrible, right? I mean, it's just such a. It presumes that I hope this isn't like that, right? Because it presumes that there's some kind of principle, some kind of. Here, you're coming from the world of geometry and categories. Please do not categorify. These structures either exist or don't exist. You're certainly not going to get anything by uplifting something to category.
well,
it's just overused, and I think it's definitely poor physics, and I suspect it's not very math either.
Never mind the word.
Okay. So don't. I think it's just don't. Say, you can decategorify something, yes. Forget about structure, but you certainly cannot discover structure that isn't there.
I mean, what happens if you decategorify your theory?
I don't think decategorifying is particularly interesting in this context. Okay, let's not get into it. Yeah. Okay. Let's discuss this over dinner or after the talk. So we'd have what's the analog of the difference in the world of schobers? Namely, you take the cone of a map. So you have let's say x and y in some triangulated category C. You can take the cone. Notice one striking difference in this world. X, y, a minus b, you can just do that. Here, to take the cone, you need to have a morphism. So somehow, one of the interesting things which happen when you try to find categorifications of formulas in linear algebra is that whenever you have a difference and you want to categorify, there must be a natural morphism along which you can take the cone. You can take the zero morphism, but that's a bit boring and usually not very interesting. So, and this is what will happen in a minute when we try to. Up there, we have a difference in the formula for the Perverse sheaves. We need to have a morphism along which we take the cone. And that's the following definition of Kapranov-Schechtman. So a perverse schober on C, let's say with zero stratification, and maybe encoded on the one spider G1. So there will be a different definition of schober depending on your choice of skeleton. They are all equivalent, but you need to choose one skeleton. We're beginning with the simplest skeleton, which was this one. Perverse schober on there, what is that? Is an adjunction. What's making that noise? Please don't do that. So you have an adjunction between two categories. I'm using the controversial notation B for vanishing cycles and N for nearby cycles, because phi and psi for me just can't denote categories. And then I have functors. So a priori I would just have a diagram, right? But what does it mean to have an adjunction? An adjunction means I have a natural transformation from the identity on V to GF, which is the unit, and I can take the cone of this. This is in the triangulated category of endofunctors of V. And this I want to be invertible. An invertible endofunctor. So the maps along which we take the difference here are given by the unit and also the co-unit of the adjunction. Identity N. Let's take, say, the cocone. I mean, there's a difference in convention if you want to take the cone or cocone, and I want both of these to be invertible. So that's the definition of a perverse schober on C, and this is called a spherical adjunction. And spherical adjunction. And these were around before people spoke about perverse sheaves, perverse schobers. They were somehow discovered, I think, a mirror symmetry from these Lagrangian spheres, and they're around a lot, and we'll see that in an example. And they were studied before people cared about their relation with Perverse sheaves. Say again? The inverses? This is a condition. This is an injunction, this is a datum, and that's a condition it needs to satisfy. What's the question?
How should I think about it?
This definition?
I understand what's a junction. How should I think that the cone is inverse?
Well, it's the monodromy of the local system of.
Yeah.
You think of this as a Perverse sheaf, but you can't. So somehow we can't define Perverse sheaf directly. Perverse sheaf of categories. So we describe it using this trick, using this theorem in terms of its sections on the skeleton, and then this datum here describes somehow this intangible abstract schober which exists, which has a monodromy around 0, is encoded still in this concrete junction.
Yeah, I guess I don't need to.
Maybe give a definition. I'll give an example in a second. Then you have your answer. It's the Dehn twist around the sphere. So, okay. Example 1, which is like the easy example, is minus signs. Minus signs just turns into a map along which you take the cone. I can't make a statement. I don't think that's particularly common. Yeah. No, there's plenty of ones which don't come from injunctions. So trivial example is this one, where V is 0 and you have N, which is the nearby cycles, and this is the constant schober. Constant. It's an injunction. This functor is adjoint to the monodromy is this autoequivalence here, which is this one.
Monodromy is not part of the data. Data is just an injunction. It has to satisfy a property that the codes on the unit is vertical. Then you will define the monodromy to be those codes.
Exactly. Thank you. So this is the constant Perverse schober. In analogy with Perverse sheaves, you define the constant Perverse schober as this spherical adjunction with stalk n. Example 2. And now we're getting back to our Lefschetz fibrations. If you have this adjunction between the derived Fukaya category of the fiber, that's maybe one geometric interpretation. I want to think about Perverse schobers as being an analogy with Perverse sheaves. And some of this philosophy of categorification actually tells you a lot of things in this context. Sure. Right.
And then, even at the end of that, there's a question. Is the monodromy a monodromy?
Yeah, it is, yeah.
It is.
But it's two different monodromies. One is the Perverse sheaf theoretical monodromy, one is the geometric monodromy, but they turn out to be the same, actually, which is great.
That's because you like
So yeah, we have the spherical object here. This is the spherical object adjunction. SI is a Lagrangian sphere. This adjunction is a spherical adjunction. So what's these two autoequivalences? They're called the twist and the co-twist. So what will be true?
I mean, that you have because in particular, right?
Yeah, sure.
I mean, there are many branches cycles which aren't spherical, and monodromy.
No, I mean, if you have a Lagrangian sphere that always, if you have a Lagrangian sphere that always gives you a spherical adjunction. Yeah, of course. No, which is not a sphere, then typically it won't be. No. For Pn, there's a different thing you can do actually, but yeah, actually, it's of course not every adjunction is spherical.
This is just a supposed example, right? If you did
This is example 2, yes. Exactly.
If you go outside the whole spherical.
No, the point is that Perverse schobers are always spherical locally. Not so. I mean, one thing which is very interesting, which comes from changing the skeleton. We'll see that next. Somehow, if I can have a very trivial adjunction as input, this adjunction, change to a different skeleton, and then get very interesting categories out of that. We'll do that in a minute. So it's not just about how complicated is this adjunction, it's also how does choosing a different skeleton then produce interesting categories. So let me explain to you why spherical adjunctions come from spherical objects by computing here the twist and these two autoequivalences. So the cone of the identity to Rhom Si, tensoring with Si, this is just the same as tensoring with the R end of Si, which is k plus k shifted by minus n plus 1. We had an n minus 1 sphere. So this cone is in fact the inclusion of the identity into the identity plus the shift by n minus 1 plus 1 minus n plus 1. So this is the shift by minus n plus 1. And this is clearly invertible. And then the cocone of the other thing, which was Fg, goes to the identity. I can't describe it quite explicitly, but it's the Dehn twist. Twist around Si. So it has a geometric description, which is also an autoequivalence. Okay, that's maybe the important example to know. So now, next we want to look at the different skeletas, the end spiders, and I don't want to give you the entire definition, but so there's a definition of schober, definition of Perverse schober on the end spider. Spider in terms of constructible sheaf plus cosheave on the end spider. So, right?
You always have the other adjoint.
Yeah, actually, spherical functors are very magical. They have all adjoints in both directions, left and right. Yeah, they're compositions with these monodromies with the left. So the left adjoint is the same as the right adjoint up to composition with the monodromy. Oftentimes it is, yes. Yeah. So I want to define now what's the perverse schober on the end spider Gn. Let me just tell you that it's a constructible sheaf of cosheave, sheaf and cosheave on this graph, on the end spider, which again satisfies which satisfies similar conditions as before. You know, we had this Fi, Gi is the identity, and so on. You can make sense of these conditions in a categorical way, and you get a well-defined theory. Let me just give you an example in a minute, and before that, tell you somehow who worked this out. So there's, I think, the first. For n bigger than or equal to 1, you have no minus signs. Actually, right, exactly. It's actually. Well, the categorification, nevertheless, is more complicated because you get some technical conditions. I don't want to get into it. We can maybe discuss it later. Yeah, it's more difficult than the case n is equal to 1 for other reasons. So there's work by Dyckerhoff, work of mine, and work joined with Haydn and Schuh. So Dyckerhoff, he has a paper on what's called the categorified Dold-Kahn correspondence. In this paper, he describes a construction which allows you, in particular, to produce these categories in these adjunctions, which give you a sheaf and cosheave on the end spider, which exactly categorifies a perverse sheaf. This was then more formalized in one of my papers, and then also further worked out in a joint paper with Haydn and Schuh. Just to mention that. Let me give you. The statement is there exists a definition. For the end spider, only for perverse sheaves, not for schobers. So the categorification is non-trivial. There's definitely non-trivial stuff you have to work out, and it's some of these 3 papers which do that. And let me. Yeah, we also do stability conditions, but that's so the paper was about an application of this schober story, but we also needed to work some foundations out for some reasons. I could, it would take 10 minutes and we wouldn't learn anything new, I think you can imagine the definition. And it's what you imagine up to technicalities.
Does the resulting thing describe the category?
Sure, yeah, it does. Let me do the example, which I only wanted to do one very easy example, which somehow gives you an idea. And then I'm telling you there's a general story which I could define, but I don't want to because I want to talk about other stuff instead. So let's start. We have that schobers on the one spider are in bijection with schobers on the n spider. I can choose my skeleton arbitrarily, and this should matter for the theory, right? So what's the schober on the one spider? On G1, let's use this one, which is the trivial one. Which schober does this give me on the n spider? It gives me the following. Let's do G3. It gives me, so I get the derived category of, let's do it easier. Let's do the derived category of the field K here. I get the derived category of the A2 quiver, and I get 3 adjunctions with the derived category of the field. Right, this is my ribbon graph looks like this. There's a category here in the middle, and then 3 adjunctions with the categories at the outside. Let's call them F1, G1, F2, G2, F3, G3. And what are the functors? So I'll write this here.
You got this from bringing together like three regular single fibers.
It's these. So in the
So yeah, so
this case, in this case, it's these Lagrangians here. Axes? All right. So what are the functors? Let me just define them. And this is, so F1. So the derived category of the A2 quiver, what are its objects? It's just A goes to B, where A and B are in the derived category of the field. So it's some, yeah, it's a representation of the A2 quiver in the derived category. I just wanted to justify my notation. Okay, this maps it to say the cone of F, and then the right adjoint G1 of K will be 0K. F2 of AB, let's say this is B, and then G2 of K will be KK, and F3 of AB will be A, and G3 of K will be K goes to 0. And in terms of the partial Fukaya category of the trigon, these are the 3 Lagrangians you have there. Compare with this picture. Yeah, exactly. F goes inside. So I guess I can erase that. But I could also do, instead of taking the derived category here, I could take the rep Fukaya category of the fiber, and then I get this category here in the middle. I'm just tensoring. Let me summarize what I just did. The upshot is, or the summary of what I've tried to teach you so far, is that the derived Fukaya-Seidel category is global sections of a perverse schober, F on what graph? There's a little caveat. Before we had this graph, but actually I need to add one extra leg. The category here is the AN quiver, but on the n spider I get the AN minus 1 quiver. So I need to add one extra external leg corresponding to the stop at infinity if you want. And I have a perverse schober on this, and this describes the Fukaya-Seidel category. And here, the fibration, it is singular there, there, and there. It's not singular here. And what the theory of perverse schobers does to me, it tells me if I have a non-singular region in my disk, the sheaf should be constant, the sheaf of categories. And by abstract nonsense, this theory tells me what category I need to put there. Namely, I put there the AN quiver. And for me, this is somehow how this worked. I knew I should put there the AN quiver, and then I looked into the Ganatra-Pardon-Shende paper and found it there. And you can guess how your sheaves of categories coming from Fukaya-categories look like from the theory of Perverse schobers. So the value at v infinity is dictated by the theory of schobers, by this rule of how do you pass between a schober on the one spider to the n spider. There's a general rule, and that tells you how you get the value here. And it matches the construction coming from symplectic geometry.
Dictated by the schober. So the name of the schober includes categories
On all the edges and categories on all those special points, except
No, also here.
including.
Yeah, then I also have a value here, which is just, again, the replica category of the fiber.
I see. And by saying that the value at infinity is dictated by
At v infinity, at this vertex v infinity. So a priori, there are plenty sheaves of categories on this graph, many of them. And Perverse schobers are a very special kind, with very special properties. And Lefschetz fibrations give rise to such Perverse schobers. And by knowing that, you restrict the domain or region of possible sheaves of categories you have to worry about a lot to very special kinds with very special properties. And for instance, if you know that somehow there's nothing singular supposed to happen at a vertex, then you kind of already know the value. It's like a version of the AN cover in your fiber. The stalk. Yeah, you know the stalk of the sheaf, the value. When I say value, I mean stalk. Yeah, the stalk, exactly. Thank you for that, for that point. That's kind of nice to have. Right.
I don't understand. What is, I mean, I can imagine, putting on top of this list some arbitrary Fukaya category, and I can tell you that very well things happen at those mark points, which are not at all self-similar. So, like, you must be putting in a ton of data to draw this conclusion. Like,
Which?
there are many. So,
what do you mean?
Say in the world of that we're studying, there are many Fukaya categories that live over this.
Right. With the Lefschetz fibration or more general?
current statement of Lefschetz. Current statement is only about Lefschetz fibration.
I see. With the spherical functors and all the stuff.
However, same statement is true for any symplectic fibration. It's more or less by the same thing. Except that you have to put now at the x's the Fukaya category. You put the Fukaya category of the free image of that piece.
Yes.
So yeah, the proof I explained somehow maybe assumes we're in Lefschetz fibrations, maybe the most familiar and straight up setting. But yeah, as I learned today from Vivek, you can generalize this story substantially. You don't need to assume you have a Lefschetz fibration specifically. You can have a more general type of symplectic fibration. And then you still have a decomposition like that, and you take the inverse images, Fukaya categories of the inverse images, and these still assemble into a type of categorified Perverse sheaf.
It's still a Perverse schober, but different data. Yeah.
It won't all be spherical objects. They will be more interesting categories.
Not just that, right? You have to specify the monotony. Somebody has to specify
You have to specify monotony known to the kind of inclusion.
yeah, I guess that's not. Yeah, good to know how they all feed into some point. Yeah.
Higher dimensions, we will not be working with an exit category of skeleton, but something else.
No, in the higher dimensions, you'll also be working with the exit category of a more general skeleton.
Okay, thanks.
Yeah.
But the statement that it's just a pair of functors f and g, that sounds very spherical, right? Well,
It's just spherical functor.
But not every spherical functor comes from a spherical object.
The functor is spherical.
Not
a spherical object.
There are spherical junctions which don't come from spherical objects.
But is the claim still that this will cover like arbitrary
Any symplectic vibration over it's more or less constant of GPS. That doesn't get us any closer to doing things anymore.
Yeah, you're saying it's in high dimensions. But yeah.
Higher dimensions is a different order of magnitude.
If you want an example of a non-trivial spherical functor, you have so evaluation of global sections at the external edge, very fancy terminology, is the cap functor. the cap functor takes an element in the Fukaya-Seidel category and intersects it with the fiber at infinity. This functor is a spherical functor.
I know, but again,
right.
I'm trying to say that there are many kinds of mirrors to many flops are just not two different things. It's just not going to look like the Kapranov thing.
Right.
Kapranov things are very, very special. There are some super,
Why does that do with vibration of the surface?
because I can put many things like fiber over there.
Every.
What does that do with flops?
Well, the question would vanish with those special forms. So if you take your fiber,
Ich habe auch noch jede Menge Zeit.
Okay, have a symplectic lasagna, or just a symplectic piano.
What is it? 12 space and what is it? Okay. I'm not exactly possible.
So PN objects.
And have such a thing shrink. It's not very obvious it's possible.
If you, there's an example, an answer for PN object, and if you have a PN object, you don't get a spherical. So let's say I have the derived Fukaya category of the fiber, and I have a PN sphere, not a PN sphere, a PN object, PN Lagrangian in there, and I get a spherical adjunction between. Don't nail me down on the details. I believe it's something like dual numbers, which maps K to P, and that will be a spherical adjunction. So even PN objects fit into spherical adjunctions, but your category of vanishing cycles won't be the derived category of the field, but a more interesting category. This is worked out in a paper by Ed Siegel. The exact category you'll find in that paper.
That's no contradiction. That's just saying the back category of the thing is something more complicated.
I mean, for example, the way to generate an example, take our thing and make a mistake. Think about it. Instead of like Lefschetz vibration, way where you project everybody to the double plane. So there are lots of examples which are going to have isolated singularities in the double plane and crocodiles and fiber. I mean, not crocodiles, nice things, but fiber are complicated things there.
Every such thing is there's no contradiction. No contradiction. It's just a category which is associated with this piece of more complicated.
Nevertheless, actually, Perverse is quite the special setting in which lots of special properties hold, which is nice, very nice. Okay. One thing I also want to mention, which is somehow we'll generalize to surfaces in a minute, but here already on the disk, we something we gain over, say, Seidel's description, directed category description, is that we can choose any skeleton on choice of skeleton. So you don't have to, this is one choice of skeleton, you could choose a different one, and then you get a different way to compute the same category, and this might be helpful. So that's already one cool thing about this theory, just for the disk. Now we want to go to surfaces. So how does that work? So let's say S is what I would call a marked surface, which means it's a compact-oriented topological surface. Compact surface with non-empty boundary. Boundary has to be non-empty, and M is a set of stops, a finite set of stops in the boundary. And then you choose a skeleton, G inside of S. One example, let's say I put a stop here and a stop here, then this would be a choice of skeleton. It needs to be homotopic to the surface, and also the external edges match the number of stops. You choose a skeleton like that. Then you get a notion of Perverse schober. Perverse schober, parametrized by the graph. Parametrized by the skeleton G. What is it? It's a sheaf plus cosheave on the graph, which it's locally perverse as before, as perverse as before. So locally means at every vertex of my skeleton of my graph, I mean, I'm on an n spider. This is the 2 spider, this is a 3 spider, and then locally on each spider, I want to be a perverse schober as I didn't define it earlier. And again, this theory will not depend on your choice of skeleton, but you need to choose one to compute it. And if you have a Lefschetz fibration,
Being a perverse schober is property.
yes, of a sheaf of categories on the graph or skeleton, right? It's a local property, in fact. Exactly. And this property ensures, in particular, that I can change the skeleton, and there's a canonical way to transport it along chains of skeletons.
And the number of the stops have to match what?
The number of external edges, right. And then when you compute the global sections, you compute like the partially wrapped thing with these stops. If you remove stops, you still have the same category of schobers. You're just somehow computing a different wrapping with a different type of wrapping. This is also the example. If you have a Lefschetz fibration, x to s to the surface, Lefschetz fibration, which gives you a perverse schober.
You put one stop at least on each tower.
That would be good, but you don't have to. Then you get the wrapped Fukaya category.
Oh, I know.
No. I mean, on the annulus, you could just do this one. That still gives you a well-defined theory.
Yeah, but you never succeeded with my guy.
No. Yeah, you lose the information in some sense if you remove stops, yeah. But then actually, no. The schober remains the same, just the computation.
No, I don't believe you that you're going down that.
Well, you need to choose. I mean, the Fukaya-Seidel category doesn't depend on where I put the stop, right? Well, what's the question?
What kind of graph do you yourself draw
For the annulus?
Yeah, like
Any graph which is homotopic to the annulus.
let's return the question like this. What kind of graph do you yourself draw?
Any contractible graph. And it may touch the boundary, but it doesn't have to.
What's an example which doesn't touch?
So if you have this, and then you have 2 vanishing spheres in some category, you have a sheaf on that, and you take the pullback, that gives you like a.
How do you go from the data which has the graph with question boundary?
Excuse me?
So your claim is that any skeleton, any of your graphs, data that well, let's say another one, right?
Right.
Okay. So how do you go from the data of this guy, the data of the standard guy, and vice versa?
Right. Well, removing the graph, removing external edges, just taking somehow a kernel of the functor here, and adding. So there's locally this is what somehow these 3 papers work out. That locally your perverse schober is described by the schober on the disk with any choice of skeleton. On the one skeleton, it's a spherical adjunction. On the n skeleton, it still comes from a spherical adjunction. Sorry. So if I have this, locally I have a spherical adjunction. And then there's a formula which allows me to produce a schober on the n skeleton using as input this spherical adjunction. It will need like a choice of total order of the edges, but that's the results independent up to some equivalence. So actually, you don't need this choice of input, but there's a formula. Yeah. And that's the main, I think, one of the main things which goes on in these 3 papers. Right. Okay, excellent. So, at some point I have to decide how much I'll go over time. I take feed input for that decision. Okay, let me just mention one thing, is that when you do this, the level of computability which you have for the Fukaya-Seidel category, you retain this here. You can still by working with sheaves instead of cosheaves. So what's the global section of a sheaf? And then I'll tell you a little bit about the new stuff, which is high dimensions. But I won't tell you anything super interesting. But okay. So global sections of a sheaf. This is the same thing as a compatible family of local sections. And this is not true for cosheaves. Cosheaves are kind of describing a global object in a cosheaf is complicated. Describing a global object in a sheaf is just gluing together local objects. So a global section, this is an element in the triangulated category, is a compatible family of local sections which are local elements. To give this example of matching spheres, matching sphere, say you have your skeleton locally looks like this. And here you have the derived category of the Fukaya category of the fiber. Here you have some categories V and V prime, which map there. Then you have some other functors. This is your sheaf. If I want to construct the matching sphere, I need to give you a global section. And how I do that is I give you a section here, I give you a section here, and then the gluing condition is that the images of the sections here coincide. So there would be the vanishing sphere Si would live in this category V. And similarly, Si would live here. I guess they are the symbols. So Si tilde, S. And they both get mapped to Si. And then the other condition is that they're also mapped to 0 by the other functors. And if you have that, you can glue these together. You have this picture where here you have Sj tilde, which is mapped to Si is equal to Sj, and mapped to 0 and 0 here. You have this picture where you have Si tilde mapped to Si and 0, 0 here. And then on the overlap, you just have Si, which is Sj. And given this, by abstract nonsense sheaf theory gluing, you get an object, a global section, which is the vanishing, which is the matching sphere, matching n sphere. For instance, proving that it's an n spherical object is not very difficult, and you get an explicit, or I mean, you can make these computations very explicit and also formalize them somehow using an infinity category theory. So infinity limits. So one thing I want to tell you about is that, or I just want to advertise, is that infinity categorical limits can actually be very explicitly computed. There are some tools for that. And they allow for explicit computations, also geometrically meaningful computations and constructions, such as matching sphere constructions.
You have the actual proof.
What does that mean? Like in the
You have an algebraic object and it's a geometric object. Yes. Well, of course the answer is yes.
Let me see. How would there are definitely some papers with such results then are then possible to prove. Maybe in general, I'm not sure.
I know a proof, but it's pretty annoying.
Well,
I don't know the symbol.
do you know that if the cone of the thimbles gives you the matching sphere, is that known symplectically?
I mean, how's it?
You have two thimbles.
Maybe.
If you have that, that's then you can prove that that result. Yeah. So I don't think there's a really, maybe there's some problems with it. Another thing which these schobers do to answer to that or say something related to that question, you can look at schobers which are not geometric but which are purely algebraic, which don't come from Fukaya categories. And if you're like me, also interested in representation theory, you can play around with schobers which behave like Fukaya categories, but they're not behave like Fukaya categories in a symplectic sense. And also purely algebraic constructions, like saying
They're not known to be Fukaya categories, or they're just not?
I mean, like the two periodic category of the field. It's just not really a Fukaya category, is it? well, in some sense,
It's not Fukaya category once.
right? Yeah. Okay. Sure. I mean, every category is Fukaya category in the suitable sense, probably. But in like, at least I don't need to worry about this question. If it's a Fukaya category or not, I can just work with it. Coming from it. Also, yeah, you can do spectral stuff as well, spectral Fukaya categories without thinking about Fukaya categories, just using the general theory. And also algebraic constructions, like say you want to compute a quotient category, you can, or work equivariantly, these constructions you can do without worrying about geometry, focusing on the algebra and the sheaf of categories. And so for certain applications, somehow just treating this theory of perverse schobers in and of itself, not worrying about the geometric origin, can be very productive. That's one thing I want to just say without maybe going into too many more details on that. So let me conclude in my 1 minute. I'll go a bit over time. So with an outlook.
Is there any specific thing you can do using this technology that you can't do just using Fukaya categories?
Just, I mean.
Like a new calculation. Okay.
So some.
I suppose it's equivalent.
It's easier. It's definitely easier to do some computations. I mean, I wrote this paper with Hayden and Shu where we described some space of stability conditions. For instance, one thing we proved is that for every curve in a surface, you get a Lagrangian by essentially parallel transport or some matching sphere analog. And then one thing you need as an ingredient to prove that the space of stability conditions is described by, well, quadratic differentials. And you needed to know the statement that if you have two different curves, they do not give you the same object in the category if the curves are not homotopic. And the curves can be arbitrarily complicated, essentially. And then proving that symplectically, I'm not sure how exactly you do that, but then categorically, there was somehow a very, using this gluing of global sections argument, there was just a way to do that, to argue that algebraically. And we could prove the theorem because of that. So there's definitely like applications which you can have with that, serious applications.
At least 10 more minutes left.
Great. Thank you. Yeah, excellent. Yeah, I think 10 minutes will be about what I need to, and about the computability maybe. Also, when you have these matching sphere constructions, the HOMs, which are the directed construction in the Fukaya-Seidel category, you can do analogs of that. Also, you can glue HOMs. If you glue objects, you can glue HOMs in the same way. And you get analogs of these directedness computations in that setting. I can tell you maybe more about that at another point. But yeah, for computations, this global theory on surfaces is not much worse than on disks for Fukaya-Seidel categories. Okay. I think I said fairly quickly all I wanted to say about that part. And I wanted to now get to the outlook on higher dimensions. And this is somehow a very difficult world in which we've only started exploring things. And I want to just focus maybe on one phenomenon or one interesting construction in this context, which maybe highlights some things which happen, but yeah, it's nothing comprehensive, I'll be able to say. So, namely, I want to focus on the following stratified space. Yeah, so we consider the stratification 0, includes in C, includes in C2, includes in C to the n. And there's a theorem about perverse sheaves. Theorem, again by Galigo, Granger, Maisonneuve.
I don't understand why you agree with these guys.
Has he written it down? No, that's a different one. The gluing, no. Right, the first one I said at least. I was not quite sure. This one I maybe isn't sure. They also prove another theorem. It's very okay. Anyway, so perverse sheaves on C to the n in terms of this stratification is the following. It's a sequence of vector spaces. How do we call them? Let's say V0, V1, V2, up to Vn. We have maps F1, G1, F2, G2, and so on. And now they satisfy the following conditions. So firstly, as before, fi gi minus the identity and gi fi minus the identity are invertible. So somehow we have a bunch of perverse sheaves on C. And then there's an additional very interesting condition, namely that fi plus 1 composed with fi is 0. And gi, sorry, chalk's not good. Gi minus 1 composed with gi is 0. What does this tell you? This means you have a chain complex, and a cochain complex of vector spaces. So to categorify this, and yeah, you may not like the term, but somehow in these examples, this has been a very productive philosophy to take this notion and then look at the categorification, which is a categorified chain complex, and then discover structures which you wouldn't discover otherwise. I mean, I'm not sure what implication there is of the existence of these structures, but to find these structures somehow has been productive to look at it like that. And so what's a categorified chain complex? And it turns out that to talk about a categorified chain complex, you can make the most naive definition work, and it is the correct homotopy coherent definition. So a categorified chain complex is simply a sequence of stable infinity categories such that d squared, so this is an element in the triangulated category of functors from A2 to A0. This is a zero object. So it's just a zero functor. But being a zero functor is a universal property, and requiring the differential to satisfy this universal property. And this gives me a good definition of a categorified chain complex. So right. So in joint work with Tobias Dyckerhoff and Walde, we looked at so a perverse schober on C to the n. We defined perverse schobers on C to the n and studied them on C to the n is a chain complex, a categorical complex. A star in degrees, let's say n up to 0, with differential is a spherical functor. And we produced a bunch of examples of such chain complexes from different directions. And since this talk is about Lefschetz fibrations and schobers from there, I want to explain how Lefschetz fibrations give you examples of such chain complexes. So, example. So you start with, let's say, x0, pi 0 to C, the Lefschetz fibration with fiber x1. Then you have x1, pi 1 to C, fiber x2. And you can continue, but maybe that's enough for the moment. Then so you start with the Fukaya-Seidel category of, let's say, x2, in which includes which has a map, right, the web Fukaya category of the fiber, sorry. No, I want to start, I guess, with x0. Into the Fukaya, there's a map. It's the Kap functor, which goes from the web Fukaya category of x1 into the Fukaya-Seidel category of x0. And then there's a localization from the Fukaya-Seidel category of pi1 onto x0. And this is what I define my first differential to be. Then I have the rep Fukaya category of x2, which again embeds here. And then there's a theorem that this is a localization sequence. There's a proof in Ganatra-Pardon-Shende. I'm not sure if they're the first. And then Seidel also proved, I think, something like that for Fukaya category analog. And then maybe that's, I could continue with the Fukaya-Seidel category of pi2 if I had a Lefschetz fibration pi2, and so on. And because this composite here is 0, this d squared is 0. So
What's happening in the geometry? I'm not following. You got it.
right, I have iterated Lefschetz fibrations on the fibers, and then I'm constructing a complex of categories out of that. And someone uses these Fukaya-Seidel categories and the rep Fukaya categories of the fibers, and it just the differential squares to 0 is a well-known fact from complex geometry about Fukaya categories. And then these differentials are also spherical functors. This is essentially, this functor here is spherical. It's the cup, it's the cup functor. And then using the sphericalness of this, that this is a localization, you can also prove that this functor is spherical. So the upshot is, if you're given a sequence of Lefschetz fibrations, you get a chain complex of categories, which defines a Perverse schober on C to the n in this sense. And there's a fun example for mirror symmetry, which is what I want to conclude my talk with.
By the way, what is the cohomology?
The naive cohomology in this degree is just the rep Fukaya category of x0. Good question. Okay. It should whatever it is, it categorifies the, well, it's not clear. But if you do the vector space analog of this chain complex, you just get the chain complex which is quasi-isomorphic to the singular chain complex of x0 under some assumptions maybe. So we do now x0 is x, y, z. I think I misread the time. I'm just now 1 minute over time. I thought I had 10 minutes left. So actually, yeah, I don't have too much more to tell you, but I completely somehow got confused with the time because we started 10 minutes late. Right, didn't have to rush quite as much. So let's do this with the Lefschetz fibration. Pi 0 is x plus y plus z, and then so x1 will be an elliptic curve. That's mean. Come on. With 3 punctures.
Sorry, even with this example, like in which sense can you
Sure.
there's say you put a potential or a fiber support. So in physics there's one potential. The only sense that I know that where you have not like more than one is if you have almost none. In other words, you just have like a very potential that I'm not really.
I have no idea about physics, but often when people study Fukaya categories, they do this.
So how do you?
For example, you have 7 potentials on x0, just restrict.
I mean, in principle, right? Potential enters your it's actually the definition of the floor.
It depends if you use the Fukaya-Seidel category or the Fukaya-Seidel category involves potential.
I know, but in which sense you have more than one? What do you do?
You choose a function on the fiber.
And rapid order.
Well, one way they rise if you have a multi-potential, like map to a Lefschetz fibration to C to the n, you also get this.
Okay.
But this may be more restricted assumption because map to C to the n, of course, is somehow more data. But let's do an explicit example. We have elliptic. I'm not sure how many else. I really can't. Okay, anyway.
It's not getting better.
Anyway, so what's the Lefschetz vibration here? To see, let's say this is pi 0 inverse of 1. And then you have x plus y. Is it? No, x minus y. And then x2 is 3 points. And I guess you stop there because there are no more interesting Lefschetz vibrations. And then what's this complex? So the Fukaya-Seidel category of pi 0. This is derived category of coherent sheaves on P2. There are 6 vanishing cycles for this Lefschetz vibration.
Sorry, slow down. So, okay, I think I have 0 with pi 0. How is x1 related to it?
X1 is the fiber over 1. Then you can check it's an elliptic curve with 3 punctures. And it itself has a Lefschetz vibration to see with 6 vanishing cycles. And then you get the Fukaya-Seidel category of pi 1, which you can compute. We do that in the paper. It's derived coherent sheaves on P1.
Sorry, what does it mean? It's fiber over 1 where?
We're doing iterated Lefschetz vibration.
Yes.
Yeah. So the terminology is still the one on the left hand of the left hand side of the board, I guess.
So you have, so you start with x0 going to C, and then let's say I take 1 as the regular fiber over 1. I'm assuming 1 is not a singular value. I have x1 is the fiber, and then that has another Lefschetz vibration to C, which is pi 1. This was pi 0. Then I again take the fiber over 1, and I get x2, and so on. Right. This here terminates after x2. So and then the Fukaya-Seidel category of pi 0 has a mirror interpretation. It's coherent sheaves on P2. Fukaya-Seidel category on P1 has also a type of mirror interpretation. It's 3 copies of the derived category of coherent sheaves on P1. And then the final one is just 3 copies. It's glued together with a semi-orthogonal decomposition. Yeah, it's true. Yes, it is. And how this arises, or what happens is you have a type of, or what we propose how to interpret this example. There's P1s, there are 3 lines in P2 form a normal crossing divisor in P2. And these together, which each intersect in a point, and you build out of this a cube of categories. What's the question? I'm saying the Fukaya-Seidel category of this Lefschetz vibration stuff. Yeah. So this is like a mirror symmetry for chain complexes, or for categorical chain complexes. And we also give it somehow a construction of the mirror, which is, I already wrote here the equivalences, using normal crossing divisors in P2. And so, I mean, a general thing to maybe ask is, can you lift some mirror symmetry equivalences to complexes of categories and normal crossing divisors? Yeah. So that's one interesting example of this chain complex of categories coming from Fukaya-Seidel categories. I think that's maybe all I wanted to tell you about this so far. So yeah, thanks for listening, and sticking around to the end.
Got a lot of them actually. So I'll be happy to break it out.
Go ahead, Jasper.
So you said in higher dimensions.